Civil engineering is in charge of a variety of plant items and systems, which include foundations, concrete and steel structures, buildings, and underground networks. It all starts with subsurface investigations. Soil investigations include topographical, geological, geophysical survey, including collection and analysis of soil samples. The purpose is to obtain a good understanding of the soil characteristics and variability over the plant area. It is also to identify any geohazard, such as collapsible soil, as well as any potential presence of a river stream and the level of the water table. The soil investigations identify the depth of the good soil, which will define the plant finished level. At this point, the grading plan can be issued, and the first site activities, which is called site preparation, can start. The soil investigations also result in the issue of the geotechnical survey report. It contains the design basis for foundations, whether these foundations shall be shallow foundations or deep foundations. What is the soil bearing capacity? And this allows civil to start with the next activity, which is the design of equipment foundations. This design requires information from equipment vendors. The required information is the equipment setting plan, which indicates the number and position of anchor bolts, as well as the load of the equipment on its foundations. The foundation size is determined in order not to exceed the maximum soil bearing pressure, and so that the equipment will not slide and will not turn over. The input data is the soil data and the loads. Load combinations to be considered and formula to be met for stability are specified in the applicable code. Once the right size of foundation is found, the calculation note is issued. It includes the input data, and it shows that all design criteria have been met. Once the calculation is done, the drawings can be issued. There are two different drawings. The formwork drawing, which shows the overall size of the foundation, as well as any pocket that is required for future inserts in the foundation, such as anchor bolts, when these anchor bolts are not cast at the same time as the foundation. And the reinforcement drawing, which shows the position, section size, and number of reinforcement steel bars. The civil engineer of the EPC contractor does not always perform the design of foundations. Indeed, the design of foundation has to be, by law, compliant with the local code where the plant is being installed. And the EPC contractor civil engineer is not always familiar with this code. Therefore, it often employs a local engineering office to perform the design of foundations. In this case, the EPC contractor civil engineer stops at a guide drawing, such as the one shown here, which shows the equipment setting plan and the loads. In other words, all the input data. Besides construction drawings, civil also needs to specify the types of materials to be used at site, as well as any particular requirements to the works themselves. This is done by issuing a civil works specification, such as this concrete works specification. As you know, concrete is a mixture of sand, aggregates, water, cement, and admixtures. All these materials need to be specified, and this is the purpose of the concrete works specification. One such civil works specification is issued for each type of work. The quantity of each type of work also needs to be quantified in order to issue inquiries to potential construction subcontractors. This is done by means of the issue of the Civil Works Bill of Quantities. Civil Works subcontractors will be asked to indicate the unit price for each line item. Indeed, Civil Works subcontracts are usually placed as unit rates contracts, which means that quantities are remeasured at the end of the job and subcontractors are paid on the actually installed quantities. Steel structures include process structures which support equipment as well as pipe racks. The input of their structural design is the geometry, which is defined by plant layout, and the loads. Equipment loads are obtained from equipment vendors. Pipe loads are obtained from piping discipline. Pipe loads do not only include empty pipe weight and weight of fluid, but also the horizontal forces due to the pipe expansion. Besides loads from the pipes themselves, the design of the pipe rack takes into account the loads due to the wind as well as to seismic action where it is applicable. Not all loads are applied simultaneously. The code specifies the relevant combination of loads. Steel structures are designed using a computer software in which the geometry as well as the loads are input. The software calculates the stress level in each member as well as the horizontal and vertical deflection. The steel structure design is accepted once the stress level in each member is safely below the maximum stress level for the selected grade of steel, and once the maximum horizontal and vertical deflections are not exceeded. Then the calculation note as well as the design drawings can be issued. These are called design drawings as they do not show all details. In particular, they do not show the details of the connections between steel members, the number of bolts in particular. This will be left to the steel structure manufacturer, which will perform these calculations and issue all the detailed drawings, including piece marks, that will be used at site for erection. Besides large process structures and pipe racks, there are numerous small structures. These are the small platforms for operator access to instrument, and equipment. All these small structures are designed in the same way, according to standard drawings. The design of buildings starts from their functional requirement. For instance, a building housing rotating machinery with an overhead bridge crane for maintenance, for instance, or a building housing electrical or instrumentation equipment. The civil engineer groups such requirements in the architectural drawings. These drawings show the building dimensions as well as the different rooms, any particular requirement such as a bridge crane, false ceiling, a false floor. The civil engineer of the EPC contractor usually stops here. He does not perform the detailed design of the building. This is usually done by the one that will construct the building construction contractor. The building construction contractor will prepare all the detailed drawings and all the bill of quantities in all disciplines, including structural, electrical, HVAC, plumbing, and so on. These drawings will be reviewed by the civil engineer of the EPC contractor, who will mark up its comments. Typically, these comments will include the provision of openings in the floor and the walls for cable entries into buildings. All what is in the ground is the responsibility of the civil engineer. It includes items which are fully defined by civil, such as foundations, as well as networks from various disciplines, including process and piping for process and utility lines, electrical and instrumentation for cables, safety for firewater distribution network. The civil engineer has to coordinate the design of the networks of these various disciplines in order that underground networks do not interfere and that there is enough spacing between these networks. The spacing is required to allow repair of one network without disturbing the others. Such coordination is done by civil by preparing the General Underground Networks Drawing, also called the Underground Composite Drawing. It shows all underground constructions and networks. Let's have a brief look at the various underground systems to better understand their contents. Let's start with the first one, which is designed entirely by civil, Rainwater Collection Network. The rainwater collection system, for instance, is a rather intricate collection of catch basins, pits at every change of direction to be able to clean in case of blockage. In fact, there is not only one such system, but two systems in a process plant. One for clean water, collecting the water, rainwater on building roofs and roads, and one for oily water, collecting water on the paving of process areas. So you see that this system of rainwater collection is rather complicated. Let's now look at the process drainage system. A process plant requires two process drain systems, a closed drain system and an open drain system. The closed drain system, shown here in red, collects liquids from process equipment which have hazardous vapors. These vapors need to be safely disposed of by burning at the flare. The open drain network, shown here in green, collects non-hazardous liquid from process equipment. For example, the water used for the periodic hydrostatic test of the equipment. The open drain network also collects small oil spills that could happen around equipment and are collected in equipment drip pans. The open drain network also connects with the rainwater collection system in the paved process area. The open drain system leads to the wastewater treatment plant, where oil is separated from water and water can be disposed outside the plant. Underground cable systems include direct buried trenches or concrete trenches. Direct buried trenches are used outside paved areas, since there is no paving, so access to the cable is possible. When there is a paving, cables have to be run inside a concrete cable trench with a removable cover. Underground cable systems also include duct banks for road crossing, as well as cable sleeves for the cables to go from the concrete cable trench up to the equipment through the paving. As you see, the underground cable systems entail quite a number of elements. In addition, there are different cable systems, including electrical power supply cables, electrical lighting cables, instrumentation and control cables, fire and gas detection cables, as well as telecommunication cables. The firewater network entails a looped firewater distribution ring, together with numerous isolation valves, hydrants which have to be accessible from the road. As you see, we have seen that there is a number of systems: the rainwater collection systems, the process drain systems, the underground cable systems, the firewater systems. All these systems have to be coordinated by the civil engineer. The precise positioning of all underground networks requires the issue of large-scale drawings. These are the civil area drawings, also called civil works installation drawings. The plant territory is divided into areas as shown on the key plan. For each area, an area drawing is issued, which will eventually show all the underground constructions and networks in this particular area. Nevertheless, these constructions and networks are progressively designed. Therefore, these area drawings will be subject to revisions, numerous revisions. They will be issued in the same sequence as the works at site. Their first revision will be for equipment foundations only. Then they will follow the work sequence for the installation of undergrounds at site, which proceeds from deep to shallow. The next issue will therefore be for the next layer above the foundations, which is the main headers, such as the sewage header and the rainwater distribution header. The following revision will be the sewage branches and the firewater branches that come just on top of the headers. The following revision will see the cable tranches which come on top of these pipes networks. Finally, the last revision will show all the surface elements such as cable sleeves, pipe support foundations, small process drain lines, and so on. The cinematic that follows will show you the growth of the contents of one civil area drawing over its various revisions. As for steel structures, concrete also includes small items such as pits, anchor bolts, and so on. Therefore, a set of standard concrete drawings is issued. This completes the presentation of the various aspects and the work of the civil engineering discipline. Thank you for your attention. Goodbye.